Okay, so now you have seen many examples of building matrices that represent linear transformations. But we have always been working with geometric arrows, with vectors. But actually, I kept promising you in the previous videos that vectors could be much more than geometrical arrows. Yeah, if I remember correctly, I even mentioned that I would blow your minds as to what vectors could be. But I haven't delivered on my promise so far. So let me do an example of a matrix that acts on polynomials. Yeah, so we are going to write a linear transformation which is going to be the derivative. So the derivative is a linear transformation that can act on polynomials, and since it's a linear transformation and polynomials can be seen as vectors, we are going to write it as a matrix. Okay, so let's look at this. This is a problem in your problem sheet, which is problem 13. Okay, so problem 13 starts. Consider the vector space of polynomials of degree equal or smaller than 4, using the bases 1x, x squared, x cubed, and x to the 4. So those are going to be our basis vectors now. Okay? Answer the following. A. Is the derivative of a polynomial a linear transformation of px in this vector space? So is it? Let's find out. So a linear transformation, so a transformation A is linear if and only if the transformation applied to a linear combination of vectors is equal to the linear combination of the transformation of the individual vectors. Yeah, that's the definition of linearity. Now, can we apply it to the derivative? So the derivative with respect to x of a polynomial px is linear if and only if the derivative of a sum of polynomials, so we could write alpha times f of x plus beta times g of x. So now f of x is a polynomial and g of x is another polynomial. So is this equal to alpha times the derivative of f of x plus beta times the derivative of g of x? Yes, it is. This is one of the rules of derivatives, right? They are a linear operation. So the derivative is a linear operation. Okay? So that's part A. So yes, derivative is a linear operation. So now part B says, if so, obtain the matrix which represents the derivative. Interesting. Okay. So let's remember, how can we be talking about vectors if we are talking about polynomials? Yeah. So remember, a polynomial of degree equal or smaller than 4, p of x, in general can be written like this. It's a0 plus a1 times x plus a2 times x squared plus a3 times x cubed plus a4 times x to the 4. That's the general way we can write any polynomial, right? So the a0, a1, a2, a3, a4 are the coefficients. They can take any value. Yeah. But this way of writing should ring a bell. This is very similar to when we were writing a1 times e1 plus a2 times e2 plus a3 times e3. Yeah, it looks very similar. So the basis vectors are our powers of x. And by the way, we need to include a zeroth basis vector, yeah, which is 1. And this was given in the problem. So the problem said using the basis 1x, x squared. And then the coefficients are simply the coefficients of this vector, yeah? Which means that using this, let me remove this line. So we can write a polynomial as a vector. So we can write it as a vector p with the coefficients a0, a1 up to a4 in the basis of 1x, x squared, x3, x4. Yeah? So you agree with this. And this fulfills all of the axioms of a vector space. You can check them. There are 10 axioms. All of the axioms are fulfilled, which means that polynomials can be written as vectors. So if the derivative is a linear operator that can act on polynomials, this means that we can find a matrix for this derivative, right? So let's do it. This time we are not in the x hat y hat basis. So in order to find the matrix A, which represents the derivative, yeah, what we need to do is we need to find the different columns which are the transformation, in this case the derivative, applied to each of the basis vectors. So in this case the first column will be the transformation applied to the basis vector 1. The second column will be the transformation applied to the basis vector x. The third column will be the transformation applied to x squared, then to x cubed, and finally to x to the 4. So since we have 5 basis vectors, yeah, we have 5 basis vectors, e1, e2, e3, e4, and e5. So each column of our matrix will be the transformation applied to the corresponding basis vector. Yeah, that was the rule for building a matrix corresponding to a linear transformation. So what's the transformation of 1? So this means what is the derivative? So remember, our transformation is simply the derivative. So what's the derivative of our basis vector 1? So what's the derivative of 1? It's 0. Yeah. Now what's the a of x? So that will be the derivative of x. And what's the derivative of x? It's 1. What's the transformation applied to x squared? The derivative of x squared equals 2x, and so on. Okay, so we found the 5 columns which should now go into the matrix. But now, of course, okay, so should we write our matrix like this? A equals, the first column is 0, then 1, then 2x, then 3x squared, and then 4x cubed. So this is not a matrix, because what we need to do is we need to express each of these terms as a vector using our basis. Yeah. So what do I mean by that? What I mean is that 0 is actually 0 times 1 plus 0 times x plus 0 times x squared plus 0 times x cubed plus 0 times x to the 4. Yeah. Therefore, this is the vector 0, 0, 0, 0, 0. And that will be, so I wrote it as a row because I don't have space, but that will be the first column. It will be a column of all zeros. Then the result, the transformed version of x, which is the derivative of x, which is 1. So that's equal to 1 plus 1 plus 0x plus 0x squared plus 0x cubed plus 0x to the 4, which is equal to the vector 1, 0, 0, 0, 0 as a column vector. I use the t as the transpose. We will see later that transpose just means flipping the rows with the columns. And the only reason I'm doing this is because I didn't have space to write the column. Yeah. Okay, so 2x, that's 0 times 1 plus 2 times x plus 0x squared plus 0x cubed plus 0x4, which is equal to the vector 0, 2, 0, 0, 0. So we do the same with all the others, yeah? So now we have the 5 vectors corresponding to the transformed version of each of the basis vectors in our basis. Right? Are you following this? This is incredible. This should be blowing your mind, I think. At least it blows mine. So now we can write the matrix, finally, putting those vectors as the 5 different columns. So how does this matrix look like? It looks like this. 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 0, 0, 0, 3, 0, 0, 0, 0, 0, 4, 0. And this is the matrix. Okay? So let's do a test. Let's get this matrix. Do I have more space? Oh yeah. So let me copy this matrix into the next page. So let me multiply this matrix times a vector. Yeah. So let me multiply this matrix times a polynomial. So let's say let's say we want to find the polynomial, the derivative of a polynomial equal to 3 plus x plus 3x to the 4. Okay, we want to find that derivative, but we are going to use matrix. We are going to use linear algebra. So this polynomial can be written as a vector, right? And what vector is it? This is the vector 3, 1, 0, 0, 3. Okay, so we are going to multiply a times this vector. So I'm going to use the trick for multiplication, the visual trick of moving the vector here, up here. Yeah. So we leave a gap here. Now, what's the size of this gap? So remember, for each row, we need one element. So we have 1, 2, 3, 4, 5. So we have 5 elements. Yeah. Because the result is a polynomial and it's written in the same basis. Okay. So those elements will be the coefficients of the polynomial. So now, to calculate each element, we need to do the dot product with the corresponding row and the corresponding column. So I'm going to do only the first, and then the rest I will go fast. So the first would be 0 times 3 plus 1 times 1 plus 0 times 0 plus 0 times 0 plus 0 times 3, which is 1. So I can now do the rest of them. And I get this vector 1, 0, 0, 12, 0. Okay? So we started with this vector v, which represented our polynomials, and we ended up with this vector w, which is a times v, which is equal to 1, 0, 0, 12, 0, which it represents a polynomial in the basis, right? So in the basis 1x, x squared, x cubed, and x4. If we write it as a polynomial, so w gets converted into a polynomial, which is equal to 1 plus 12x cubed. So now I got a question for you. Is 1 plus 12x cubed the derivative of 3 plus x plus 3x to the 4? Yes, it is. So this is working. So we have written the derivative as a matrix operation. Yeah. So great. Here I have like a Venn diagram showing what's happening. So we have the input space on the left, which is the input space of the polynomials of degree up to 4. Yeah. And we are applying this transformation A, which is the derivative, and the output space is this space of polynomials. So notice one thing. The reason I did this diagram is because the last row of the matrix was all zeros, which means that the last element of the output vector is always going to be 0. So we could say, okay, we could remove that row from the matrix and say that the output, when we multiply A times a vector B, the result will always have one less element. So we will get a polynomial instead of degree 4, it will be a polynomial of degree 3. And that makes sense because when you do the derivative to polynomials of degree 4, the result is always a polynomial of degree at most 3. So I like to see how things make sense. So I hope now you have a greater respect for linear algebra in general. So it's not only vectors, it can be much more. Thank you very much.